What if we have one end that is free and one end that is fixed, like what we see here? At the fundamental frequency, we are going to have a node at the fixed end. So this is the fixed end. And we are going to have an antinode at the free end, resulting in getting only half a segment at the fundamental frequency. Now, half a segment, that's lambda over 4. Remember, one segment is lambda over 2. Half of that is lambda over 4. So if we measure the length of our device, our string or rod or whatever is oscillating at that frequency, now that length is equal to lambda over 4. So we get lambda from that. That's the fundamental frequency, or what we call the first harmonic. What's interesting is when we go to the next mode, we still have a node at the fixed end, and we still have an antinode at the free end. So we can fit, when we fit a node in the middle, we end up having a segment and a half, or in other words, the length of the string is going to be 3 lambda over 4. Okay, remember that for all waves, we have this relationship. We said that for the fundamental frequency, lambda over 4 is equal to L, which leads to lambda is equal to 4L. And for the second mode, what we just have here, 3 lambda over 4 is equal to L, which leads to lambda is equal to 4L over 3. Let's use these in this equation. Remember what's the same in this equation. What's not going to change between the fundamental frequency and the next mode? What's not going to change is the speed of the wave, meaning lambda times f is going to be the same. Lambda 1 f1 is lambda 2 f2, because lambda times f is equal to the velocity. For the fundamental frequency, for lambda, we had 4L here. So 4L, that's lambda, times f1 should be equal to lambda 2, which is what we got here, 4L over 3, times f2. You notice here the 4L's cancel out, and we end up having f2 is equal to 3 f1. I hope that you notice that's why we have m equal 3 here. So actually, we skipped a harmonic. We don't have a second harmonic. We went from the fundamental frequency, instead of doubling the frequency for the second harmonic, we went straight to the third harmonic. That's the frequency that we get for the next mode. Okay, now I'm going to erase all of this and get back. Okay, so at the fundamental frequency, what we have m equal 1, the wavelength we said is 4 times L. At the next mode, that will correspond to m equal 3, we are going to have a wavelength that's equal to 4L over 3. Now the relationship for all frequencies are going to be f sub m is equal to m times f1, where m's are only odd numbers. So it's going to be 1, 3, 5, 7, 9, etc. Then the value for the wavelength is given by this. Remember, we always have this expression. That's always true. Now, going back to the graphs, at the first harmonic, we have a node at the fixed end and an antinode at the free end. For the first overtone, so we are using a new term here, so it's the next mode, what we call the first overtone, which is the third harmonic. The third harmonic is the first overtone. At the first overtone, we still have a node at the fixed end and an antinode at the open end, but we have a node at the middle. For the next overtone, the second overtone, we'll add another node. So we have two nodes in the middle, still a node at the fixed end, and an antinode at the free end. So overall, we have here 2.5 segments. At the next overtone, we add another node. So 3 nodes, 3 antinodes, 3.5 segments, etc. Now we added a new term that we call the overtone. The overtone can be compared to the harmonic, but there are some differences. A harmonic is an integer multiple of the fundamental frequency of the vibrating object. When it was fixed at both ends, or when it was open at both ends, the harmonics were integer multiples of the fundamental frequency. So we had f1, and then f2 is equal to twice f1, then f3 is equal to 3f1, etc. So all harmonics are integer multiples of the fundamental frequency, or the first harmonic. Overtones, however, refer to any resonant frequency above the fundamental frequency. So they are above the fundamental frequency. The first overtone starts here. So that's our first overtone. Now, an overtone can be a harmonic, like here. The first overtone is the second harmonic in this case. However, when we have something fixed at one end and open at one end, we are going to skip harmonics, but we do not skip overtones. The next resonant frequency is the next overtone, but we are not going to have twice f1. So in other words, all harmonics are overtones, but the other way around is not correct.